Have you ever wondered why the world doesn't just collapse in on itself? Or conversely, why it doesn't fly apart into a chaotic dust? It is a magnificent mystery. If you look at a glass of water, it looks smooth, doesn't it? But we know that if we look deep enough, it is a jiggling, bumping crowd of tiny particles. It is a wonderful thing to ask, what are the rules of this game? How do the pieces move on the board? It is a little difficult to begin at once with our modern view, which is quite strange and bend the mind a bit. So let's take a step back. Let us look at the world as it appeared to physicists around 1920. It was a comfortable picture, a sensible picture. And then we shall see how we had to take a hammer to it. In those days, the stage upon which the universe performed its play was a three-dimensional space of geometry, the kind Euclid described. The actors on this stage were particles, atoms and such, and the medium in which they changed was called time. Now, these particles had properties. The first was inertia. This is a very simple but profound idea. If a particle is moving, it keeps going the same direction forever, unless, and this is a key, unless someone or something pushes it. That push is what we call force. Back then, we thought there were two kinds of forces. First, there's this enormously complicated, messy interaction that held atoms together. The thing that decided if salt dissolves fast or slow. We didn't understand it very well. But the second force we knew beautifully. It was a smooth, quiet, long-range attraction called gravitation. It was elegant. It followed a simple rule. The pole gets weaker the farther away you get, specifically by the square of the distance. But here's the catch. Nobody knew why. Why do things keep moving? Why is there gravity? We didn't know. We were just describing nature, not explaining her ultimate motives. From this view, imagine the air in this room. It is a gas. It is a myriad of moving particles, rushing about, banging into things. When you stand by the seashore and feel the wind, that is just a drift of atoms moving in one direction. When you feel the heat of the sun, that is the random internal jiggling of the atoms. And if I clap my hands, I create a pile of excess density, a crowd of particles pushing their neighbors, who push their neighbors, a wave rushing outward. That is sound. It is a tremendous achievement of the human mind to connect the crashing of the waves, the warmth of sand and the sound of the wind to motion of tiny, invisible specks. But were these specks? In 1920, we thought there were 92 kinds of them, 92 different atoms. We gave them names like oxygen and carbon. But the question remained, what holds them together? Why does carbon like to hold hand with two oxygens to make carbon dioxide, but refuses to hold three? Is it gravity? Absolutely not. Gravity is far, far too weak. If gravity were the glue of atoms, you would fall to the floor. So, we must imagine a force that acts just like gravity, getting weaker with distance, but is enormously, wildly more powerful. And there is one other crucial difference. Gravity is always attractive. Everything pulls on everything else. But this new force, electricity, has two personalities. We call them positive and negative charge. And the rule is simple. Lights repel and unlights attract. Now, think about the implication of this. Suppose you have two unlike charges, a plus and a minus. They attract each other powerfully and stick very close together. Now bring a third charge nearby. Does it feel anything? Practically nothing. Why? Because the pull of the plus and the push of the minus cancel each other out almost perfectly. This is the secret of a universe's stability. Atoms are made of these fiercely interacting plus and minus parts. Protons in the nucleus and electrons whirling outside, but they are so neatly balanced that, from a distance, they seem to have no hold on each other at all. Let me give you an example to show you just how monstrous this electrical force is compared to gravity. Imagine two grains of sand, tiny things, just a millimeter across. Put them 30 meters apart. Now, let's imagine that we took away the balance. Suppose everything attracted everything electrically, just like gravity. How much force would there be between those two tiny grains of sand? Would you guess a pound? A ton? there would be a force of 3 million tons between them. It is staggering. 3 million tons of pull, locked inside 2 grains of sand, hidden by the perfect cancellation of plus and minus. If you were to stand an arm's length away from someone, and you had just 1% more electrons and protons, the repelling force would be enough to lift the entire Earth. This is why you don't see electrical forces in everyday objects. The balance is so precise that we only notice gravity, which is actually incredibly weak, puny little force in comparison. Now, let's look closer at these atoms. By 1920, we had a picture of a nucleus at the center, heavy and positively charged, surrounded by light negative electrons. Later, we found the nucleus itself contains protons charged and neutrons neutral. We number these atoms. Carbon is number 6. Why? Because it has 6 protons inside and 6 electrons outside. The chemistry, how it behaves, how it burns, how it smells, depends almost entirely on those electrons on the outside. So, really, the whole list of chemical elements could just be 1, 2, 3, 4. Oxygen is just element 8. It simplifies things, doesn't it? The universe is just counting. But we need to talk about how these forces travel. We used to think, I put a charge here and it pulls a charge over there. Direct interaction. But that turned out to be too simple. Imagine a pool of water. There's a cork floating near you, and another cork farther away. If you push the water near your cork, the other cork eventually moves. If you look only at the corks, you might say, this cork pushed that one. But we know better. You disturbed the water, and the water disturbed the second cork. Electricity works the same way. A charge creates a condition in space, a distortion. We call this the electric field. If I shake a charge comb, I distort the field. That distortion ripples out like a wave. If I have a piece of paper nearby, it will wiggle. But here's the fascinating thing. There's a delay. The wave takes time to travel. If I shake the comb back and forth, I send out waves of electromagnetic influence. If I shake it slowly, say 100 times a second, that is like the hum of electricity in your walls. If I shake it 1,000 times a second to kill a cycle, I am sending out radio waves. I am on the air. Shake it faster, 1,000,000 times a second, and we have FM radio and TV. Go faster still. Shake that comb at 500 trillion times a second. 5 followed by 14 zeros. And something miraculous happens. Your eye detects that wave. You see it as a color red. Shake it faster, you see blue. This is all light is, the shaking of electromagnetic field. It is the same stuff as radio waves, just wiggling faster. Go higher still, X-rays, then gamma rays. They are all the same family, just different notes on the same piano. Now, this was a picture in 1920. It was beautiful. It was unified. And then it all fell apart. Just after 1920, we discovered that the rules of the game change completely when things get very small. Newton's laws, inertia, forces, they are wrong in the world of the atom. This is where quantum mechanics enters the stage. And it is strange. It is so uncomfortable because it behaves like nothing we see in our large-scale world. First, we learn that the idea of a particle having a specific place and a specific speed is impossible. This is the Heisenberg uncertainty principle. You cannot know where something is and how fast it is moving at the same time. The more you know one, the less you know the other. This solved a terrible mystery. If opposite charges attract, why doesn't the negative electron just crash into the positive nucleus? Why doesn't the atom collapse? Classically, it should. It should spiral in and boom, end of matter. But it doesn't. Why? Because of uncertainty. If the electron fell into the nucleus, we would know exactly where it was in the nucleus, and that it wasn't moving. That violates the rule. The electron must have some uncertainty. It needs elbow room. So it jiggles. It cannot sit still. It hovers around the nucleus, compromising between the pull of the electric charge trying to drag it in, and the uncertainty principle forcing it to keep moving. That jiggling motion is what keeps atoms huge. Huge compared to their tiny nuclei. It is what makes matter solid. You are solid because your electrons are frantically jiggling to avoid violating the laws of quantum mechanics. But there's a deeper, more philosophical shock here. Science used to be about prediction. If I set up an experiment in Stockholm, and then I set up the exact same experiment in Quito, I should get the same result. That seems obvious, right? Quantum mechanics says, no. If I set up a single atom ready to emit light, I cannot tell you when it will happen. I cannot predict which direction the photon will go. Nature, at her bottommost layer, is not deterministic. She is probabilistic. We can only predict the odds of something happening. This bothered philosophers terribly. They said, science requires that the same conditions produce the same results. Well, nature doesn't care what philosophers think is necessary. If we do the experiment and the results are random, then that is the truth of the world. We must accept it. We found that waves behave like particles, and particles behave like waves. Light is a wave, yes, but arrives in packets, little bullets of energy we call photons. Consider the electron. We use the picture as a tiny, hard bullet, whizzing through space like a planet in miniature. A simple, solid thing. But when we look closely, that solidity melts away. If you fire electrons at a barrier with two holes, they don't pile up behind the slits like gravel. They create an interference pattern, bands of light and dark, exactly like ripples crossing on the surface of a pond. How can a single bullet go through two holes at once and interfere with itself? It implies that the distinction we made, is it a wave or is it a particle, was a false choice all along. The electron is neither. It is an excitation, a field, a ripple in the fabric of reality that can act like a rock or a wave depending on how we ask the question. This realization leads us to the crown jewel of modern physics, quantum electrodynamics, or QED. It sounds like a terrifying name, but it is simply the story of how light and matter interact. It is the most precise theory in the history of science. When we say it explains a burning of fire, we mean it explains a frantic exchange of energy between oxygen and few electrons. When we speak of the color of a rose, we are describing how photons of light hit the petals, how the electrons in a rose's atoms jiggle in a specific rhythm to absorb the blue and green and bounce back only the red. The hardness of a diamond is nothing but the stubborn refusal of carbon electrons to let go of their neighbors. QED shows us that chemistry is just physics acting on the outer shell of the atom. And since biology is wet, complicated chemistry, and life is the organization biology, then the rules of life itself, the way your muscles twitch, the way your nerves fire, are ultimately the rules of these dancing electrons. But the theory whispered a secret we didn't expect. The mathematics demanded balance. It told us that for every particle in the universe, there must be a mirror image, a twin with the opposite charge. For the electron, there is the positron. It seemed like a mathematical ghost until we actually found one. And the rule is dramatic. If matter shakes hands with antimatter, they vanish. They annihilate perfectly, transforming their entire mass into a burst of pure energy, gamma rays. So, look at where we have arrived. We started in 1920 with a stage made of rigid geometry and actors made of solid, distinct rocks. We have ended up in a universe of shimmering probability. We found that solid matter is really just a vibration in a field, a collection of uncertain clouds held together not by rigid hooks, but by a frantic, perpetual dance to avoid the laws of certainty. We have traded the dead clockwork of the past for a living, breathing, uncertain world. And frankly, isn't that just a more marvelous place to live?
You have just experienced an adaptation of the first chapter from the legendary 1963 book, The Feynman Lectures on Physics. We are just beginning this journey through the laws of the universe. So please subscribe and turn on notifications. Your support is greatly appreciated.